you get homework on MDP conservation processes, again on Blackboard, and then last release project 2, which will basically ask you to put game research on Pac-Man. So essentially now Pac-Man is the next program. Okay. So that's coming up. And then one other thing I wanted to mention in case you are actually reading the textbook and are confused is that the whole discussion of finite horizon MDPs is not actually present at any length in the textbook. There are like a million different types of MDPs, as I mentioned. One, and it's just that they directly, the textbook just looked at infinite horizon MDPs. We'll get to that, but I think it's actually much easier to understand infinite horizon MDPs if you understand finite horizon MDPs. Okay, basically you do the same exact thing as the finite horizon MDP value iteration, and just instead of thinking that each iteration has some physical significance in terms of the horizon left, number of steps to go, which is what finite horizon does. In the case of infinite horizon, you do the same value iteration and you just think it's an iteration. It's like an internal thing for the program, and then you keep iterating until the value function converges, which we'll get to today. But that's very much the way we'll get to value iteration. And also, it's actually useful to understand the differences between finite and infinite horizon MDPs because they actually wind up having a lot of conceptual insights. Okay. So, are there any questions before I get started? Okay. So, this is just a quick summary of what we did last time around towards the end of our class. We talked about policies for MDPs. If you have an MDP, then the solution for an MDP is a policy. And it turns out that policies depend a lot on whether, for example, you have a finite horizon MDP or an infinite horizon MDP. For the case of finite horizon MDP, you will have a non-stationary policy in the sense, normal policy, which we first described as, is just a mapping from state to actions. Okay, and if it's only mapping from state to actions, since there are A actions that you can do in each state S, then essentially the number of policies in the worst case would be A times A times A times A times A, S number of times. So it will be A power S. Okay? That is basically, it turns out that is actually only true for stationary policies. That means policies that don't depend on how long you have left to live. Okay? And it turns out that for infinite horizon, that is actually true, because it turns out that when you have infinitely long to live, then if you have lived 35 years, how much time do you have left to live? Infinite. If you have lived 29,000 years, how much time do you have left to live? Still infinite. So essentially, there is no notion of non-stationary policy for infinite horizon MDPs. But if you have finite horizon, if you can only live for 100 years, then it does make a difference as to the optimal action you should do in a state does depend on whether you are young, middle-aged, old, which is basically what we are talking about. Okay, so when you wind up having non-stationary policies, notice that instead of the number of policies being A power S, which is for stationary case, the total number of policies being A power S for stationary case, for non-stationary policies, it would be what? There are A power S policies for each amount of horizon left. That is, if you have 100 years left to go, then you have A power S policies for what to do when I have 100 years left to go. When I have 99 years left to go, I have another A power S policies. When I have 98 years left to go, I have another A power S policies. So basically, what you have is A power S times A power S, etc. T times, where T is the horizon, total horizon. Okay, which is nothing but a power T S. So the strange thing is the number of policies is larger if you live finite amount of time. You kind of knew this, like gods have it easy, gods to live for infinite amount of time, essentially they only have to deal with one optimal policy. You guys, on the other hand, have to deal with a much larger space of policies. And each policy itself essentially have to tell you that the size of each policy itself is larger, because the policy has to tell you for each state and each amount of time left to go, what is the optimal action, what's the action supposed to be. Okay, so we will actually, one of the things that you want to have in the back of your head is the seesaw between finite horizon and infinite horizon case. On one hand, finite horizon looks like a harder case, right? Because there are many more policies. But on the other hand, it turns out that value and policy iteration for finite horizon actually are much easier to understand. Okay, and then when you go, but you can build on that to go to the infinite horizon policies. There is a question. Yes.
Are there some policies
There is no notion of subset because a policy has to tell you what to do in each state. Okay, there is a difference between, so a policy is a total function from states to actions. That means for each state you should know what to do. And there was a question earlier on Piazza of what is this notion of partial policy. Imagine you only figure out what to do for a set of states. What's the best thing to do for a set of states that you're likely to actually find it during execution. That would be a partial policy. Okay, one of the things that you have to wrap your mind around is it looks like we sort of made the problem much harder when we went from deterministic, when you essentially had to only know. If you think of what A-star search is doing, it's essentially saying, starting from initial state, I'll go to the goal state, and I'll just tell you what are the actions I have to do to go from initial state to the goal state. So in essence, what A-star search is telling you is the action you are supposed to do in exactly the states that you will find on your way to the goal. Do you understand what I just said? So A-star search is giving you a policy, but it's a partial policy. It only tells you what to do in the states that you are expected to go through in the optimal path from the initial state to the goal state. All the other states of the space, you don't know what to do, but you don't expect to go there. Do you understand what I'm saying? You don't expect to go there. The problem with MTPs is the best laid plans of men and mice. Essentially, you do think that I'm supposed to use this path to go from here to here, but as you start doing the actions, the outcome of the action cannot be fully predicted at the planning time. So because of which, you may very well likely reach any random state of the space. So in the worst case, you need to know what to do in every state that you can possibly reach, which basically is all possible states of the world. In the worst case. You see what I'm saying? Okay? So it's not surprising that while in this class as well as next class, we will focus on, so think about the following thing. We came to MTPs from game trees, remember? And then we tried to do online search during game trees. Okay, now if you did online search, would we have computed the full policy? No, we are computing the pieces of the policy as needed. Do you see what I'm saying? We are computing the pieces of the policy as needed. So one way you make the problem easy is to essentially only enumerate the piece of the policy that is needed. But right now we will talk about how to compute the entire policy. Okay? Yes.
So would policies for Markov decision processes be reflex agents, or?
So if you have computed the policy, then during the execution, it's just a reflex agent. But the true definition of a reflex agent is that it doesn't deliberate at all. So remember what is happening. This is a very interesting question. I hope people understand what he's saying. So in fact, you can ask, after A star search is done, and you computed the optimal path, when you are executing it, are you a reflex agent or a deliberative agent?
Reflex.
Reflex. But then you spend a lot of time coming up with the optimal policy. The true reflex agents essentially, as soon as you give them a problem, they'll start executing. So in fact, it does tell you that sometimes you can, if in fact you wind up knowing, let's say, that you'll always be living in, for example, where is the, this particular word. Nothing else, but just this particular word, where the goals will be exactly like this. Then you may as well go ahead and compute an entire optimal policy, and from then onwards, essentially you can be a reflex agent, because it doesn't matter where you find yourself in, you know what to do. This is actually the game that many people play in terms of using MDPs, for example, things like AlphaGo, etc. It looks as if they don't have any roles changing from time to time, as if they're actually coming up with a reflex agent. The reality is, the reason you're able to do is the reward function basically has been decided upfront. Changing problem means changing goals, as well as initial state. In the MDPs, if you change the reward function, then you have to compute a new policy. Do you see what I'm saying? Okay. But initial state, if you did compute a new policy for a given reward function, then it doesn't matter which initial state you are in. You know what to do. Because to some extent, you overkilled the problem. You didn't just check where you are, you saw what is the optimal policy. Optimal policy doesn't care about what initial state you started from, because it basically assumes that you might eventually get to any random state. So you might as well know what to do there. Okay? So I'll go back. Okay, so keep this in mind. The next thing, we also talked about the fact that in addition to stationary and non-stationary policies, both the type of policies we looked at then were essentially pure policies, in the sense they are essentially giving a single action to do, given a state in the case of stationary, or given a state and horizon to go in the case of finite horizon. But the question is, why not give mixed policies, where basically you give a stochastic distribution on the actions that you are supposed to do given the state. Okay, and you're computing the optimal such distribution. And I mentioned at the end of last class that in fact it turns out that mixed policies are not needed for MDPs, not necessary for MDPs. Because if there is an optimal mixed policy, there is also an optimal stationary policy. But that's no longer true when you actually have an opponent. That means it's not an MDP anymore, but it's a Markov game. In which case you do have to consider mixed policies, which we won't get into right now, but that is sort of something to keep in mind. Okay, so putting in perspective with A-star search and MDP, remember in A-star search, at planning time, you essentially search for the optimal path from the initial state to the goal state. Okay, and then in the execution time, you execute the actions on the path. One crazy thing to understand about A-star search is A-star search agent doesn't need to open its eyes during execution. Do you understand why? It needs to know the initial state. And if you know the initial state, and you have deterministic dynamics, and you have computed the optimal path, you can close your eyes and execute it. And you can just say, I'm done, I'm in the goal state. And you just make a generic statement of that kind. If in fact your world is not static, then what you did would not make you go to the goal state. But A-star search assumes that it's a static. So in fact, one of the interesting things about A-star search is people might view it either as a situation where the agent doesn't even need to have observable data of the world. They only need to know the initial state. The moment they know the initial state, they never have to open their eyes. Because I pretty much know exactly what I'm supposed to get to when I do it. You can also say, well, I just keep the eyes open just in case. No, I don't expect anything to change. I will be in the initial state, I will do action A, I will go to S1, I will do action B, then I'll go to S2, I'll do action C, I'll go to S3. I know this, but I'll just keep my eyes open. If I do keep my eyes open, I can say A-star search is just like MDP, in the sense that for the states it finds itself in, it knows what actions to do. It doesn't compute a full policy because the rest of those states that don't fall on the optimal path, it knows it will not go there. You guys understand what I just said? Okay, so that's A-star search. Okay, MDP, at the planning time, you search for the optimal policy, not a path, but a policy. And I explained to you why policy is important, because you no longer know for sure that just because you did action A expecting its most likely outcome to happen, it's not guaranteed that the most likely outcome will happen. And something else might happen, in which case you will be in a different state, and then you need to know what to do next. So you search for the optimal policy. And at the execution time, you basically observe the current state S, do the action A that the policy recommends for S. And the only difference for finite horizon is in the loop you observe current state as well as time to go, stages to go. So how many stages you have left to go? And then you look into the policy to say for this state, with these many stages left to go, what action is supposed to be. Okay? Now, you notice that this really is a clear-cut generalization of this. MDP is a clear generalization of A-star search. Okay? And keep that in mind. And one of the things that you have to start asking yourself is if in fact MDP is a generalization of A-star search, what about heuristics? You have to keep this in mind, and it should eat you. Basically, if it's really a generalization, where are the heuristics? How will not do this? Keep that in mind. Okay, so what I'm going to do then is I just need to, now with all this huge introduction, I am now known that I need to just compute optimal policy. That's what the solution is for an MDP. Okay, so the interesting thing is, of course, to talk about optimal policy, you need to compare policies. If you say something is optimal, there should be a way of comparing what happens when you if you have policy pi, which pi star is optimal, and I give you pi star, pi 1, why do you think pi star is more useful than pi 1? What is your metric? Now, in the case of A-star search, we had this issue too. If I say optimal path, what do you mean optimal path? Given two paths, how do you say one path is better than another path? How did you say it? No, when I give two paths to the goal, what do I say? How do I say one is better or worse than another? Okay, so this is not good. Because I'm going at PhD level and you are at grade school level. That's not good. So we are talking about, if I have A-star search, I'm talking about just the quality of the solution. Okay? And I come up with my A-star search, it took whatever time, and came up with path P1. And another A-star search for the same problem came up with path P2. Which one is better?
The one that's optimal and minimizes the amount of steps to go.
The cost.
Yeah.
You add up the costs on the edges. You add up the costs on the edges. You can think of costs as negative rewards. And so in some sense, A-star search minimizes the total accumulated negative reward. right? MDP is more of an optimistic guy. It tends to think of the world as positive. When you just say reward, in general you think reward is positive. You can have negative rewards, but you generally think that reward is positive. And similarly, A-star search has costs, so you assume that costs are going to be positive, means rewards are negative. Okay, so in the case of MDPs, so if I give you two paths, P1 and P2, you know how to compare by adding up the cumulative cost of the paths. If I give you two policies, how do you compute which is better? The interesting bit is that for each policy, for each state, suppose MDP1 is using pi 1, MDP2 is using pi 2. I'm sorry, MDP1, you have one MDP, sorry, there are not two MDPs. There's only one MDP. You can either use pi 1 or pi 2 as the policy. I want to see whether pi 1 is better than pi 2, for example. So imagine I start with state S1. If I start with state S1, if I follow this policy, okay, let's say I follow this policy for like either 100 steps or until I die. So I will go through some number of states. At each time I go into a state, I get a reward. I get a cumulative reward. I do this, if I just do this once, I don't know how good this policy is because the policy is stochastic. The second time I do the same exact policy, I might get a different set of states. How many of you just understood what I said? The rest of you are totally lost. Okay? If you follow the same policy from the same state a second time, you may get through different state sequences. That's the whole point of stochasticity. Please understand this. Okay? Okay? So because now our policy pi 1, I do it from S many number of times. I do it once until either I live for 100 states or basically die, and then see that total reward. I do it once more, see the total reward. I do it once more, see the total reward. Let's say I do it 1,000 times, and I take the average reward. This is called the expected reward, expected cumulative reward of following this policy from state S1. Did you just understand what I said? This is the expected cumulative reward of following this policy starting from state S1. It's not obvious. You have to kind of essentially simulate the policy many times and take the average. Yes?
So if you did something 1,000 times and calculated your expected average reward, at that point would you reevaluate and change your policy, or?
No, let's not jump there. So imagine right now I gave you two policies to compare. So to be able to find which is the best policy, first you need to know if two policies came and said, both of us are good, you have to decide who you want to. Once you figure that out, you can use that to bootstrap yourself into an approach for finding optimal policy. Do you understand what I just said? Okay, yes.
So if we go to sample and simulate, the simulators don't we fit into statistical, knowing the statistical abilities?
This is why we just say, I told you how you do it empirically, but the reality is you just take expectation, E, and the expectation is supposed to essentially do the sampling in the right way.
But don't we assume that the distribution is below A? So
Yeah, that's all fine. So that's why the next slide onwards I will put a big E, expectation. Okay, expectation over distribution. But I want, before I just put a E, and I hope that people understand, given that you guys, some of you at least don't even think that if you run the same policy from the same state, the results can be different at different times. Depending on the way the stochastic effects of that. If you don't even understand this, showing you a big expectation makes no sense. Okay?
It's my show that I don't understand this. But is this just for the finite horizon?
For everything.
So how would you then, for infinite horizon, how would you get an expected?
So your worry, presumably your worry is So first of all, the interesting question for that is the state sequence that you get in an infinite horizon case. So the point that he's making, by the way, I need to know names. What's your name?
Zach.
Zach. The point Zach is making is the idea that I gave is very easy to understand in the context of finite horizon. I said go up to 100, why 100? Okay, well if you have a finite horizon MDP that's exactly 100 horizon, then each sequence you consider would be either 100 long or less. Okay, now if you have an infinite horizon MDP, then each sequence you consider can be infinitely long. And Zach is a little worried that if you add up little numbers over an infinitely long sequence, you might get infinities. When you get infinities, things becomes degenerate because all states say we have infinite amount of cumulative expected. This is where we discount future. We'll get to that. Okay, it's a very interesting point. We'll get to that when we get to infinite horizon. But for now, sort of think of, I basically looked at sequences, of certain length, basically the horizon length in the case of finite horizon, and then he added up, the cumulative reward I'm getting. Okay, and then took the average. So we need, suppose coming back to it, phi 1, let's say said for S1, if you do pi 1, you get 4.7 on the average. And pi 2 says, if you do me on the same MDP for S1, I'll give you 4.89. Now, which is better? The second one is better. In general, given two policies, you'll say one policy dominates the other policy. If it gives the cumulative reward from each state using that policy is higher or equal to the value, the reward you get, cumulative reward you get with the second policy. Now, I have to keep on saying this thing called cumulative expected reward. Not just the reward, but cumulative expected reward. I want to make a name for it. I will call it value of a state. I will call value of a state as, with respect to policy pi, is the expected cumulative reward at S if you follow. Stare at this and make sure you understand. The value of a state is an amazing idea. In particular, let me ask you the following things. Okay? Imagine I have two states. In the same case, in the previous case, okay? In the previous case, imagine that I've decided to go with pi 2. And pi 2 said, remember for S1, the cumulative reward that you got, expected cumulative reward you got is 4.89. That means the value is 4.89. It turns out that there is an S2, state S2, for which pi 2, the same policy that I picked, says expected cumulative reward from that state is only 3.0. So that means the value of the state S1 is bigger than the value of state S2. All right? Now, what is another property of a state? In addition to value, what else does a state have? Value is something I just defined right now. Every state already has a reward. I just told you that V pi of S2 is less than V pi of S1. My question is, can you talk about RS2 and RS1? Given this, do you know how RS2 and RS1 are related? Remember that the value of S2 is lower than value of S1. Can I now say that reward of S2 is lower than reward of S1?
No. No.
How many people say no? Okay. How many people think you can say that reward of S2 is less than reward of S1? Okay. The second batch has to do work on your intuitions. Okay. The reason I'm asking, thanks for raising your voice. Thanks. The point is, reward is what you get right now. Value is what you get in long term. Every important decisions that you make, every important decision you make, policy you have, basically has to be dependent on the long term cumulative reward. And the states tempt you with rewards, immediate rewards that are actually oftentimes in the reverse relation to their long-term reward. So for example, a state where I don't eat candy in the night before going to sleep, and a state where I do eat lots and lots of candy in the night before going to sleep. Which one has higher reward? Unless you're one of those crazy people, it's clear that having candy is always good. Why aren't you having candy in the night before going to sleep? Are you like a masochist or something? You don't want to have life, happiness in life? No, you are giving up local happiness to increase your long-term happiness. People who eat candy in the night tend not to have teeth to eat candy with a few days from there. So, having figured this out, either yourself or your doctor figured it out for you, you take the hit of having, you basically avoid the siren song of this particular state saying, take me, take this particular state, it's like a great state, it has very high reward. But you don't take it because it turns out in that particular case, it turns out that the cumulative reward from that state is actually worse than this other state, which is of not eating again. Now, this also leads to a very interesting idea called reward shaping. Why not make reward system in such a way that the local rewards actually become proportional to long-term value? I am making the problem. If I am making the problem, why don't I make the rewards in such a way that the local rewards become proportional?